Yeah.
So, all right, we left off after doing 7A. So let's do 7B and 7C, and let's see if you can do, how much can you do without me saying anything on B?
Okay.
First step. Whoops, I said something. That's okay.
Derivative.
All right. So what is G prime of X?
Just write it down first.
First of all, I want you to look at that function. What's the easiest way to take the derivative of that?
Wouldn't it just be...
There's two ways to do it. There's two ways to do it. Which is the easiest one? Distributing it first or using the product rule?
Product rule.
Well, the only thing is we can distribute it really easily. Notice that if I distribute that, x to the 2/3 times x to the 1 is x to the 5/3.
Yeah.
Minus 3x to the 2/3. Now we don't have to use the product rule. In other words, now it's the sum or difference of two polynomial expressions. We can use strictly the power rule. So let's do it this way. If you see a way, now I'm not 100% convinced that this is easier than the product rule. It's going to give you the same answer, but to me, it always feels easier if I can distribute it. A lot of times you can't distribute it. If I've got something like this, well, I can't distribute that.
Yeah.
I can't multiply the x times what's there. So I can't do that. I'd have to use the product rule there. But I'm kind of a believer that if you don't have to use anything but the power rule, that's the way to make the least amount of mistakes. So what's the first derivative?
Isn't it x to 2/3?
Start with the coefficient. In other words, always start there.
Oh.
So the first number you're writing is 5/3.
Yes. 5/3.
X to what?
To 2/3.
Okay. Do the same thing on the second thing. What's the coefficient going to be?
Is it just, it's 2 and then x to the negative 1/3.
There you go. Okay. So now what? What determines whether a function is increasing or decreasing?
If it changes positive to negative?
No. It's if a function is always increasing if its first derivative is positive. So to figure out where it's increasing, I have to set that thing to be greater than 0.
Okay.
To figure out where it's decreasing, I got to set it less than 0. That's always the step when they ask you about increasing and decreasing. Is you first take the derivative and then you either set it to be greater than 0 or less than 0. Now, I think the best thing to do here, that's not trivial to solve. What are your ideas? How would you solve this? In order to find the critical points, that's the next step. You're going to have to use a line chart. Remember, whenever we're solving an inequality that involves the product or division, you're going to have to use a line chart. Now, at this point, it doesn't involve a product, but I can factor something out. What can I factor out so that I'm left with two things being multiplied together instead of two things being subtracted.
Can you factor out a third?
X to the minus 1/3.
Yeah.
The reason is that if I factor out that, I'm left with minus 2. And now I'm going to be able to make progress. So I'm going to factor out an x to the minus 1/3. And what is left? First of all, I know it's minus 2 over here.
Yeah.
But how do I figure out what's left when I factor out that?
Is it just?
You divide it.
Yeah.
When you're factoring something out, a greatest common factor, what you're doing is dividing each term by that. So I'm basically taking 5/3 x to the 2/3, and I'm dividing it by x to the minus 1. And nice things happen. Notice what happens. You end up with 5/3 x.
Yeah.
Now, if that has to be greater than 0, now what are my critical points? Critical points are pretty easy at this point. In other words, I can't figure out critical points when it's in that format. I have no idea. But once I get it to be the product, well, the definition of critical points is where's that equal to 0? Where's that equal to 0? So what are my critical points?
It's just 0 and let me grab my calculator real quick, just so I have it.
Okay.
But yeah, 1 second.
Set that equal to 0 and solve it.
So it would just be is it just 6/5?
You need to have more confidence in your actions. I would
Yeah.
rather you tell me it is 6/5 rather than saying, is it 6/5?
Yeah.
If you make a mistake, I will tell you. Trust me. I'll show you how to do it if you make a mistake. But you knew how to do this. Have confidence
Yeah.
you knew how to do it. Okay, so that's my critical points. That's the only 2 critical points. So what's the next step?
Just a line chart.
Okay, let's draw a line chart. What 2 points am I going to put on there? 0. I don't always put 0. The only reason I put 0 on there is because it's a critical point. Okay?
Yeah.
Because if 0 is not a critical point, it just kind of confuses the picture. You don't need it on there. So, next step.
Now you just take numbers that are less than 0, between 0 and 6/5, and after 6/5.
Okay, let's start with left of 0. Always go left to right.
So just -1.
Okay. That creates a little problem, doesn't it?
Yeah. So
These are not defined.
yeah.
You cannot have a negative number for x. You can have 0, but you can't have a negative number. So nothing's going on back there. Next step.
And then just 1.
Okay. So 1 becomes positive, right? In other words, 1 to the minus 1/3 power is 1. It's 1 over x to the 1/3 power, which is 1 over 1 to the 1/3 power. Well, that's 1. 1 over 1 is 1. So that's positive. What about when I plug in 1 here on the right part of that?
That's negative.
Okay, so that's negative. That means it's negative in that whole interval. And now what?
And then just 2.
Okay, 2 produces a positive there and a positive there. So it's positive here. So our answer for increasing is what?
Increasing is 6/5 to infinity.
Give it to me in interval notation. Tell me whether it's parentheses, brackets.
Parenthesis 6/5 comma infinity.
Okay, and decreasing.
A parenthesis 0 to 6/5.
Now, just for the heck of it, this is an unusual problem in the sense that we have an area that is not in the domain. And we should be able to see that if we graph it on Wolfram Alpha. We should be able to verify. Now, I know you can't use your calculator, but just for our training here, it's be nice to make sure we got the right answer. So what was it? It was x to the 5/3?
Yeah.
Oops, hold on. X to the 5/3. And what was the rest of it? Time? No, what was the rest of it? Here, I can look at it. I got it right here. Sorry. All right.
Yeah.
It's x to the 2/3 times x to the -3. X minus 3. All right, let's see what that thing looks like. Should have nothing in negative territory. Oh, it took it a long time. What in the world? Hold on. It's not x to the 5/3, it's x to the 2/3. I wrote it wrong. It's x raised to the 2/3 times x minus 3. Would make that big a difference? Would it eliminate all the negative numbers? It didn't. What's going on? How come? See, do you know these curves here? The blue is the real part. The brown is the imaginary part. So I understand why they have this imaginary part here. What I don't understand is that part.
Yeah.
How can you have a negative number for x?
Yeah.
So I must be misinterpreting a complex valued plot. Let's look at the real one only. Now look at it.
Yeah.
I did the real one only and it eliminated everything to the left of the y-axis. Not only that, you can see that it decreases from 0 to 6/5 and it increases after that. So we definitely have the right answer. And I'm quite sure if we look at the bottom of the page, what is this, 7b?
I don't understand how they're getting negative infinity to 0.
No, I don't either. Something's wrong with that.
Are they just saying that, or when we said not defined, are they just saying that it is defined?
No, I think they're wrong. I think they're absolutely wrong. Now, we didn't finish the problem. We didn't find any local extrema, and we still have more work to do that. But in terms of our intervals for increasing and decreasing, there's no way x can be negative. No. Yeah, you just can't take, x can be negative. Because you're taking the cube root of it. You can take the cube root of negative numbers. I didn't notice that first time through. I apologize. Yeah, no, they're absolutely right. We ended up with x to the 1/3 after factoring, after multiplying, taking the derivative. What do we end up with? X to the minus 1/3 times, and I think it was x minus 2.
Yeah.
That's what it was. And we had to figure out where that was greater than 0 and where it was less than 0.
It's 5/3 x minus 2.
Correct. There you go. Okay. So, sorry about that. Yeah, x can be negative. We're taking the cube root of it. I don't know what happened. I wasn't thinking. Which now leads me to believe that what's Wolfram alpha graph? Why is that only in the positive to the right of the y-axis? That's a little strange. There is something, incidentally, in higher mathematics about taking negative numbers to fractional exponents. I've been struggling with that issue for 10 years. I won't waste any time on it here, but if you do a little research on that, if you have spare time, you'll find some very strange answers as to whether or not, and let me just give you a quick sample as to why. What's that equal to? Take the cube root of -8 first and then square it.
That's 4.
Yeah, unfortunately, that's not what Wolfram alpha gives you. Wolfram alpha gives you a complex answer. And I did some research on it, and there's definitely something about taking negative numbers. It depends on the fractional exponent, but you cannot take -8 to that fractional exponent. So as long as the numerator of the fractional exponent is 1, then you can do it for sure. So the domain on that is definitely all real numbers. Okay, so let's do this part of it. Find any local extrema. Well, what do we have to do to find local extrema?
Is that the second derivative test?
The first thing you do is set that equal to 0.
Okay.
But then you have to determine whether it's a minimum, a maximum, or neither. Well, when I set that equal to 0, I get two possibilities. Right?
Yeah.
Is 2 right? No, 2 isn't right.
No.
Setting that equal to 0 is x equals 6/5.
Yeah.
So there are the only possibilities where I can have a local extrema. Because remember what local extrema means. Means the slope of the tangent line is 0. Doesn't have to be an extrema. You could have a situation like this. Okay. Well, I got 3 places on that where the tangent line is 0. I got one there. I got one there. I got one there. I got one there. I got 4 places. Only 3 of those are extrema. That one, and that one. This one is not. And so what we have to do is test both of these spots to see whether it's a local extrema or not. What's the best first test? There's 2 tests. And the easiest test, in my thinking, is the second derivative test. Because it's usually pretty easy to get a second derivative. So let's see. First derivative again was 3. No, hold on. It's the only problem with me writing is I don't have enough room.
No, that you have this first derivative up there.
I know, but it's in the form of a product and I don't want it. In other words, if I'm going to take the second derivative of it, I want it to be back in a polynomial. It'll be easy. Okay. If I have to take the derivative of this, I got to use the product rule again. So the first derivative was 2/3 x minus 2x to the negative 1/3. Was that not the first derivative? Yeah, when I distribute that out, I get x to the 2/3, which becomes 2/3 x.
Oh, I got
minus 3x to the 2/3, which becomes minus 2x to the minus 1/3. Okay, so take the second derivative of that.
Second.
Yeah, we're going to use the second derivative test to determine what these local extrema are.
Yeah, but isn't the first derivative is not correct, I don't think.
Okay, what is it? Did I do it? Yeah, it's minus 1/3 here. No, yeah. It's minus 1/3 there.
Yeah.
No, it isn't. Hold on. Oh, gee.
Wait, I'm...
This second. Okay, let me multiply these 2 together. That gives you x to the 2/3. Oh, no, it gives you x to the 5/3 minus 3x to the 2/3. And now the first derivative is 5/3 x to the 2/3 minus 2x to the minus 1/3. Do I got it right now?
Yeah.
Okay.
Yeah.
All right. And now, let's take the derivative of that. So I have 2/3 times that. That's 10/9 x to the minus 1/3 plus 2/3 x to the minus 4/3. Is that right?
Yeah.
Okay. Now, all we have to do is evaluate that at these 2 numbers. If it's positive, it's concave up. That makes it a minimum. If, well, it just says find the locations of any local extrema. Well, we got to determine that when we get a second derivative that is 0, that doesn't tell us anything. In other words, g double prime of this number, 0, is 0. So we have to use the first derivative test on that one. Okay, but let's check this one. As long as we're here, let's figure out what g double prime of 6/5 is. If it's positive or negative, then we'll be able to tell for sure if that's a local extrema. Well, what is that? That is 10/9 times the 1 over the cube root of 6/5 plus 2/3 over the cube root of 6/5 to the 4/3 power, not the cube root. I meant to put that in. Yeah, I guess I can say cube root and then take that to the 4. There we go. Is that not this?
Yeah, that's it.
In other words, is all I've taken is the second derivative and I've plugged in 6/5. And I put it in the denominator because of the negative exponent. Okay? Now, that's a positive number, correct?
Yeah.
That's a positive number. I don't have to do the math. I can see that the cube root of a positive number is always a positive number multiplied by a positive number being added to a positive number. So that's positive. So that tells me that at 6/5, the original function is concave up, which makes it a minimum, which makes it a local extrema. Now, let's go back and look at 0. When the second derivative test produces 0, then you have to go back and do the first derivative test, which is a lot more complicated. The first derivative test, basically, you have to draw a line chart and see what the first derivative does on the either side of that point. The only time it's a local extrema at 0 is if the sign changes on the first derivative, left and right. If it goes plus, 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 it's not an extrema. If it goes minus, 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 it's not an extrema. It's got to go plus, minus, or minus, plus for it to be an extrema. Okay? So, what is it to the left of 0? Now, which function am I checking? Am I checking the original function? Am I checking the first derivative? Or am I checking the second derivative?
Checking the first derivative.
Correct. I want to know, I'm applying the first derivative test. So, let's do minus 1. Analyze g prime of minus 1. And just tell me if it's positive or negative.
It would be positive.
Well, let's do it. This again introduces this problem of taking a negative number to a negative exponent, or to a positive exponent, but a fractional exponent. And then I'm subtracting 2 times negative 1 to the negative 1/3. Wow. Well, let's assume that that is 1.
Yeah.
It's either 1 or it's not defined properly. It's either 1 or it's complex, okay? So we're going to say the cube root of negative 1 is negative 1, and then negative 1 squared is positive 1. So this whole thing is 5/3, positive 5/3. Now, that is definitely negative 1. Times 2 makes it negative 2, but there's 2 negative signs, so it's plus 2. Aha! positive on the left side. Okay? Now we got to check what it is to the right of 0. So let's check g of 1 instead of g of negative 1. You with me? And if I lose you at any place, please stop me, Mitch.
Yeah, I understand everything at this point.
Get lost when I'm doing the work and I'm going maybe too fast or something. But okay, so we want to check g of 1 now. Well, that's pretty easy. That's 1, so that's 5/3 minus 2. Because 1 to the negative 1/3 is 1. And that is negative. So indeed, we do have a local extrema at 0. And what is it? Is it a maximum or a minimum? It's a maximum. It's concave down, therefore it's a maximum. And let's look at our Wolfram alpha chart just to verify that. So we had a maximum at 0 and a minimum at 6/5, right? A maximum at 0. There's our minimum. And we really should be looking at this, the blue of this right here. I don't see an absolute maximum at 0. In fact, here, let me just show you why I don't see it. I think I did my math wrong. Look at what the slopes are going to 0. They are minus, 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 correct? Yeah, look what they're coming out after 0. Plus, plus, plus.
Yeah.
Not really. Not really. If this is an
1 second, my internet may have just crashed in my phone.
I'm sorry, can you not see my screen? Did you say your internet crashed? Can you hear me? I'm gonna call you. You can hear. I can hear you, but I don't. Can you hear me? No.
Hello.
Hi, Mitch. Okay. Yeah, I knew I had lost the sound from you.
I lost the sound.
Did you just lose sound? In other words, can you still see like what's on my screen? What's on my screen right now?
The Wolfram alpha stuff.
Okay, you don't need to reset. We can finish the session just fine using the phone, if that's okay with you.
Yeah. Okay. Just 1 second. Let me put headphones in, and then I'll do what it does. Can you hear me like this?
Ooh, you might have just come back. I heard the click. Do we have sound?
That was my headphones.
Hold on. Say something. Say something.
Do I have sound this way?
No, we don't have sound that way. So let's just keep using the phone.
Yeah, I don't have sound through my computer, so
okay.
Let's do it this way.
All right. You'll notice how the bottom graph misrepresents. Now we got sound. Say something now.
Yeah, let's.
I'm going to hang up the phone. Can you hear me now?
Yeah, let's try this again.
Yeah, this works fine now. Are you hearing me? Mitch, are you hearing me? Sound went back out. Are you hearing me?
Yeah. Are you?
Okay, I do now. The sound was out for about 20 seconds after we got it working again. So I'm not sure if our audio is going to stay working. We'll try it. Let's both talk frequently, because sometimes I'll drone on for 2 minutes at a time and I discover you've lost sound. Let's go back and look at this chart. Okay. If I take this lower chart, and hold on, let me minimize my GoToMeeting so I got a little bit more room here. Let me take a picture so I can write on it. They're saying that this really should look like this. Right?
Yeah.
So what's going on at 0? Nothing. It's not even, well, nothing is going on. It's only my crooked writing is going on. That's what it's doing. And we can definitely tell that it's decreasing from negative infinity to 6/5. And then it's increasing from 6/5 to positive infinity. If we look at that chart, that's what that chart tells us. Now, why the real valued plot? Notice the real valued plot does not have any numbers to the left. So what I'm saying about taking a fraction or a negative number to a fractional exponent, that's what that's indicating. In the real valued plot, they don't do that. In the complex valued plot, they do carry the real value to the left. In other words, that's a real value there. So I'm a little puzzled by that. I'm also a little puzzled as to, we must have just made a mistake. There's the roots, 0 and 3. There's a global minimum only. The only extrema is at 6/5. There is nothing going on at 0, which leads me to believe that I must have just made a mistake in my when I did all those calculations. And it's certainly not worth our time to figure out where I made my arithmetic mistake. The main thing for you to learn here is the sequence, the method that you have to use to answer these questions. So at a minimum, let's work with C and see if we can get this set up properly. Okay? All right, first step
is to take the derivative of it.
Okay. So, yeah, really, I think the first step is to get rid of the radical sign.
Yeah.
So it becomes Z times 8 minus Z squared all to the 1/2. Notice I cannot distribute that.
Yeah.
So if I can't distribute it, give me the first derivative.
The first derivative is 1, and then it's 1/2.
When you use the product rule, it's the derivative of the first thing that's being multiplied times the second thing plus the reverse. You don't take the derivative of both functions ever together. In other words, you took the derivative of Z and you got 1. So the other term doesn't change.
Okay.
Now it's plus. Now you're not taking the derivative of Z. You're taking the derivative of the other term. So what's the derivative of the other term?
1/2. And then 8Z.
Hold on.
Or 8 minus Z.
Squared.
To negative 1/2.
What else? What did we forget to do?
Do the center one.
Right. Got to apply the chain rule. And only when we're taking the derivative of that 8 minus z squared are we applying the chain rule. Well, the inside is minus 2z, right?
Yeah.
Okay, now let's rewrite that in a little better form. We got h prime of z equals 8 minus, I don't need that 1, 8 minus z to the 1/2. And this is going to be a negative, right? Because that plus and that negative right there become a negative. And my 2z times that z is 2z squared times a half is z squared. So that gets rid of that, that, and that, all times 8 minus z squared to the negative 1/2. All right.
Yeah, that makes sense.
I gotta find out where that's greater than 0. Starting with that part of the question. We're going to find out where it's increasing. How can I find my critical points? Remember, you have to turn it into a product. We don't find critical points when we have a polynomial minus another polynomial. We find critical points when we have something multiplied by something or something divided by something. What can we factor out?
Can we factor out just 8z squared to the negative 1/2?
8 minus z squared. Now, we could factor out to the negative 1/2 or the positive 1/2. I always prefer to factor out the negative exponent because that turns that into 1. Okay, so it leaves what's left behind a little simpler to follow. So when I factor out that, what does this become?
Is that just 8 minus z squared to the negative 1/2?
No. Remember, I'm taking this term and I'm dividing it by what I factored out. Well, what did I factor out? I factored out 8 minus z squared to the negative 1/2. Same base, different exponents. What do you do to the exponents?
Don't you subtract the exponents?
Which leaves the exponent at 1. 1/2 minus a negative 1/2 is 1. That's why I like to factor out the negative.
Okay.
Because it leaves you with all of this. Okay, and then I still have this over here. Well, when I divide this term by 8 minus z squared to the minus 1/2, that goes to 1. So I'm left with just z squared. Well, that's beautiful. Now I got 8. Now I got 8. This is in the numerator, first of all. So I got 8 minus 2z squared. You with me?
Yep.
This is in the denominator. 8 minus z squared to the positive 1/2. And I have to figure out where that's equal to 0. Well, now I can find critical numbers. Let's find our critical numbers, critical points. Where are they? And critical points are whatever makes the numerator 0, whatever makes the denominator 0.
The numerator would just be 2.
Okay, so that's one critical point.
The denominators Is that undefined or no? There's.
Oh, I'm trying to figure out where 8 minus z squared, 8 minus z squared, the square root of that, what makes that equal to 0? Because I cannot divide by 0. It's when z squared equals 8. So it's when z equals the square root of 8, which is 2 root 2.
Okay.
Okay. So to me, those are the two critical points. And what you now have to do is draw a line chart. Put your critical points on there. There's 2, and there's 2 root 2. And now let's start checking numbers to see where it's positive. So check 1. And which function do you plug it into?
You plug it into the first derivative. Would you plug it in the one where it's set equal to 0, the 8 minus 2 z squared over 8 minus z squared, 1/2?
Yes, I think. Hold on a second. Let me think about this. Yeah, we're trying to figure out where the first derivative is positive, so clearly we plug it into the first derivative function. And the first derivative function is that one. Yeah, we can plug it in pretty easily. Let's plug in the number what? What's the best number to use?
0.
Good. So when you plug in z for 0, this becomes square root of 8 minus 0. So that's positive to the left of 2. Now, what's between 2 and 2 root 2? What's a nice number to use?
2.5.
Okay, I was going to say 3, and then I realized that 2 root 2 is less than 3. So we can't use.
Yeah.
So, okay, 2.5. That's a good number to use. The math becomes a little more difficult. Let me erase some of this stuff I have over here on the left. Wow. They've taught you all this calculus in 2 months. No way anybody learns this much calculus in 2 months.
Yeah, that's why I needed you, because...
Absolutely. Anybody. That's just too fast. I have no idea why they're going through it that fast. Okay, so we're going to plug in 2.5 into this function. So h prime of 2.5 okay, 2.5 squared is 6.25, I believe. 5 halves times 5 halves is 25 fourths. That's 6 1/4. Okay, so what we have is 1 3/4. 1.8 minus 6 1/4 is 1.75, and we're going to take that to the 1/2 power. And then we're going to subtract 2.5 squared times that same divided by 1.75 to the 1/2. So we got 1.75 to the 1/2. Take away, right offhand, we got 1.75 to the 1/2 power, and I am subtracting from that 2.5 squared divided by 1.75 to the 1/2 power. That's got to be a negative number. First of all, the square root of this is going to be smaller than 1.75. If I square 2.5, I get 6.25. Dividing 6.25 by a small number gives me a number bigger than the square root of 1.75. So that whole thing is negative.
Yeah.
And now to the right means we got to take h prime of, we'll say, 3. Geez, each one of these problems is like an hour problem to go through all the steps.
Yeah.
Unbelievable. Critical points are those two. So I need to plug in 3. I need to do h prime of 3. It should be relatively easy. Notice what happens. That is undefined, because when you square 3, you get 9. 8 minus 9 is a negative number, and I'm trying to take the square root of a negative number. So, not defined. The first derivative is not defined. So our answer should be increasing from negative infinity to 2. Let's see if this is the answer. Increasing from negative infinity to 2. Decreasing from 2 to 2 root 2. And that should be the answer. Let's see. 7C. Notice we didn't look at something.
Yeah.
That right there. Z, the domain for Z was between -2 root 2 and +2 root 2. So that's not even in our domain to look at. And in fact, that means the answer has to be -2 root 2 to 2 is where it's increasing, and it's decreasing from 2 to 2 root 2. That's got to be the answer.
Yeah.
No. Oh, they got it increasing from, I got it. They got it increasing in the middle and decreasing on the side. So they have a chart that looks something like decreasing their chart's going to look like this. Decreasing, increasing, decreasing. And that right there is -2 and 2.
Yeah.
And this point is -2 root 2. And this point is +2 root 2. Now, so we got 5 minutes. Let's see if we can figure out some local extrema, whether they're a local extrema or not. Not sure I'm going to be able to do this without redoing all my math. My math obviously was not correct.
Did we just mess up where, like, because when you take a square root, it's the plus and minus of the number? So did we just screw up there, or?
We never took the square root, did we? Ah, you're right. At one point, we were trying to figure out where 8 minus z squared was equal to 0. And you're right. There is a plus or minus on that. So you're absolutely right. That is where I screwed up. When I took the square root, when we solved where that was equal to 0, I didn't use plus or minus. I used plus only. I thought the answer was 2 root 2. And it was actually plus or minus 2 root 2. So that does account for the mistake. So I think we can avoid going back to scratch. However, we do have to apply local extrema, but I'm not sure I need to take the second derivative. I think we can use a sign chart. Were you even taught the second derivative test for extrema?
Yeah.
Okay.
Yeah, we were.
Okay, but they also taught you that if that produces 0, then you have to do the first derivative test.
Yeah.
Okay. Might be easier here because I think I can't. Do you have our first derivative written down by chance?
No.
Yeah, I don't have it either. That's the one disadvantage of the way I do this now. Whereas if I had my other pink one, I would have it. I may have to go back to that other method. Certainly going to work better for problems like this. Remind me of that at our next session, is to not do it on this, because I just don't have enough room to do all the calculations they want you to do. Whereas with my other method, I can scroll down. I can't erase, but I can scroll down. So I can always scroll back to figure out what I had.
Yeah.
I guess we better stop for now but you did pinpoint the root of my problem as to why I got the wrong answer, because I didn't use the plus or minus square root. I'm going to suggest you do a line chart on the first derivative and use the same critical points that we had. In other words, the critical points are going to be plus or minus 2 root 2 and plus 2 and minus 2. Those are your 4 critical points. And you're going to have to check what your first derivative does left and right of each of those critical points. If it changes sign, it's a local extrema. It doesn't even tell you whether it's a max or a min. You just have to tell it whether it's a local extrema or not. In other words, you have to determine whether the first derivative sign changes to the left and to the right of each of those critical points. That's what your job is. And that will tell you whether it's a local extrema. If it changes sign, it is. If it stays the same sign, it is not.
Okay.
Okay? So it might be worth your time to work through C and come up with all of the answers in local extrema. What we will do next time is start with 8.
All right.
Okay?
Good.
All right, Mitch. Sorry for all the arithmetic errors, but this is hard stuff.
Yeah.
I will talk to you next time.
All right. Thank you.